So yeah, I think the previous one, the question one is actually really straightforward. So let me quickly go back. Basically, yeah, well, if you want to do dot sort, that's a method that's applied to the original data. So you can see that your original list is like this, and now once you do sort with the dot, then actually the original data is modified. Okay, and if you want to do sorted, it's gonna create you an output that is gonna be different. Okay, just be aware. And similarly, you can apply sort with the dot that will directly change your combination, or you can just do sorted. Okay, so yeah, that I'm gonna keep it up for your reference. All right, so that's good. Yeah, so if you're successful with number two, then we can move on to number three. Okay. So question three, how might you modify the code below so that one fewer recursion calls are made? Check your answer with yeah, well, this is actually really straightforward. So remember, we have done the implementation from before that you do the last character move to the front. Actually, let me copy that. So, well, you can actually do it like this. So for the first element, you move to the end. Okay, that's fine. But you can also do the last element, move to the up front. So what's interesting here is that you can do -1. Okay, so that's also indicating the last component. You all the way up to that -1. So that's fine also. I'm gonna do print um reverse string. Yeah, let me give it a string so that I don't have to type many times. Yes, I am not. And who am I? So reverse S, and let me also print reverse 2. Right. So yeah, it looks fine. So you see, the only thing that we need to be aware is that okay, no matter what, here -1 is a argument actually for the indexing. It's saying it's the last one. Okay, so it basically it's actually the length of your string -1. So that's something a little bit special for Python. Okay, that's sort of like a trick. If you ever want to get the last index, it's gonna be this. But if you do s of len s, then actually that's gonna give you a bug, which is kind of uh, weird. But yeah, -1 is fine because they do this kind of default. Okay, so that's pretty interesting. And how do you make sure that there's less lines, one less recursion call? Remember, it always go down to the zero empty string. Okay, so when there's nothing, when the length is 0, of course you can reduce the last call, right? Because whenever the length is 1, I can always just return as itself, right? So let me change one of them. So I can change this. So whenever there's a length of 1, I can just so yeah, it definitely should not give you any bugs as long as your logic of recursion is fine. But then yeah, I would say you can do it yourself to get into the to Python tutor.com and see how many iterations there are. That's so far so good. So that's pretty straightforward. Coding 4, yeah, that's what we have done from last time. Basically, you just do the replacement. So I would say the string operations, they are really sort of standard, okay, but they're really helpful. And of course, for the operations or methods that's available, make sure to, if you want to do some text like data mining or data processing, make sure to search for certain useful features. Replacement is actually one of them. And basically, you need to notice that whenever there's a emoji there, there are two spaces, okay, one on the left and one on the right. So you certainly want it to be readable. You don't really want to remove both, but you want to remove at least one, and then you need to think about which one to remove. Okay, so that's something you may try and play with, which is the reason why I'm removing the one before. Okay, so that's what we have seen from last time. Yeah, one comment is that, okay, for long codings files uh, and long text files, you know that replacement of text in editors are efficient, but still now Python is a more powerful package application well, software in a sense that can help you to do automation. So you don't have to manually go through each file. So that's something you can learn after you uh, have taken the course. Just write your own script to process text files. Um, Question 5. Answer the reflection question below. Oh, this is subset sum. Wait. Oh, okay. This is the correct version. Okay, the optimal the subset sum function that will give you the true optimal subset sum. Okay, remember we have capacities. So basically, you have a capacity which is a number that you want to fulfill as much as possible, where you have a list of items with different volumes, let's say. But basically, you want to combine certain numbers from the list so that the capacity is reached or close to its to the capacity. So what they do here is that, okay, you do the strategy of looking at the first element in the list every time. Okay, so get the first element, well, the index 0 element, and then from the rest, so you can think about always putting the rest as a kind of like a sub problem, okay, a sub list that you feed into the recursion, right? But then depending on whether you keep it or lose it, right? You use the first when that's less than the cap, or lose it by just discarding it and using the rest of the list to fulfill the cap. But then, well, either one may give you a larger um, assignment, all right? And then, of course, you want the maximum assignment. So if you just do these two recursions, it will not really help you. But you do need to take the max in order to get the best possible, okay, um, assignment. So and then of course use Python 2.com and evaluate. So yeah, let's quickly. Let's did we? Okay. So yeah, I probably need to copy the code cell. I don't want this. Yeah, that's the original data. Okay, this is very good. So yeah, one thing powerful about the Colab is that sometimes it reads from the context and give you something that you want. Okay. So yeah, 41, how is it obtained? Remember, we discussed in class that 23 plus 18 is that 41. So if you actually do the greedy algorithm by just saying I select everyone, the first along the list, if it's less than cap, I keep it. If addition goes exceeds the cap, then I drop the one that I'm about to add. So that if that's the method there, then you will eventually get what you will eventually keep a 30 and then keep the 10 and then done. So that's the best possible is 40. However, 41 is actually the best possible, which is actually keeping these two. Okay. So now let's see. We want to simplify, right? So you can simplify the code. Obviously, this if statements, they only talk about the first item. So you can just make it if and then elif and then else, right? So you can do that. So that's something that you can easily modify. You can just do else. So it should not give you anything weird, right? And then let's see. Um, let's copy the code to look at the tutor. Visualize. What you need to do is to copy it here. Just make sure that your code is not bugged. Well, if it's bugged, it's fine. But if it runs forever, then they will not give you any visualization. So yeah, how many steps? Yeah, it's 258. Okay, so it's indeed a process. Okay, so let's see. Uh, so mm, let me just remove certain spaces when they're not 100% necessary. Uh, yeah, let me remove the doc string. So since it's not really essential in the code right here, so okay, now it looks a little better. Wait, where's the button? Ah, right. So I probably need to zoom out a little. Okay, so the global frame, there's only one function. So then we do the subset sum. Okay, now here the capacity, you see, whatever there's a list, okay, it's going to be in the objects. And okay, we just let it run. Okay, the capacity is, of course, greater than 0, and list is not empty. So we jump to the first, we split. Okay, so it's going to be the first and the rest. So the first is the 45 up front, and then we create another list, okay, which is the rest, which is shorter. And you can expect this once again very important. The pointers they can be multiple, but the lists they are just stored in the memory, just like okay, there's an object, there's a function, which is our subset sum, and then there are lists. Okay, this the first longest list, which is with six elements, and then five, and then we can expect. So we just move on. So now the first number 45 is larger than the cap, then we check if it's equal to the cap. Uh, so wait, yeah, right. Larger than cap, so it's dropped. Okay, so we get to this. So return subset sum, right? Return subset sum with the capacity of 42 again, and the remainder is now that fifth length. Okay, so you see there's a pointer rest referring to this list, and my list here, the current one is also this list. Okay, so that's very important here. And then we get to the first element, which is 30, and 30 is less than the cap. So if the first if, the second if, they are both false, we get to the else statement. So now be careful here. We have two lines, okay, doing the subset sum. Okay, we have the first plus. So now the first is 30. Now we get to what? We get to this is the problem, okay? So subset sum with now 42 minus 30, which is the 12 that we want to fulfill using this for list, okay? And then the next line, lose it. Oh, wait. Yeah, so that's calling the subset sum function. And okay, so the next line, that line 30, that line 13, the line 13 lose it is not even touched yet. Okay, so this is a tree. We are going, you can say this is a tree. I'm going along the depth first. So now the first element is 23, and then now the rest is okay, the three element string, and then we move on. So we look at the first element is 18, now comparing to the capacity 12. So yeah, you need to go through this at least once to see how actually Python is getting the code done. Okay, so now the first rest. Okay, so we drop, yeah. You see, first is larger than the cap. We get to return subset sum cap rest again. Okay, so it's gonna be the 12 is the cap, and that thing, the rest is now fed into the code again. 18 is also gonna be dropped. Okay, so you can expect. First now is 18. The rest is now a 2. Okay, so now you see it just systematically just decreases the size. And then the first is larger than the cap, and then return. So now you can expect that we are feeding this into the subset sum again. So now you see 12 with this. Okay, now 10 is going to be legal. Okay, so this is what's called, if you are constructing the tree, this is actually the depth first. Okay, so you go deep all the way to the bottom, and then go to the other branches. So now we have the cap of 12. The list is this. So we're gonna where are we? Okay, we're here. Okay, so now we go to split the data, and then the first if is false, the second if is false. Now here we are at use it or lose it again. So we're gonna still do the use it. Yeah, well, it's here. Okay, so now it's gonna call the subset sum. You see, if you look at the line, it's gonna be cap minus first. Okay, that's my 2. Okay, so 12, I'm keeping the 10, so I have a 2 as a remainder, but I'm using the almost the last one, which is 5. So it's always choosing the use it line, okay, before doing any of the lose it, okay, at all. And now that's only 36 steps. So where are we? Okay, we are actually, okay, we are here. So we have a capacity of 2, but a list of 5. So that's going to be dropped. So first is larger than the cap. Yes. And then you see one more subset sum. That's going what? That's going, you see, the capacity of 2 and the empty list. Okay. So this is a procedure you definitely need to go through once to see exactly what's going on. And it takes a little bit of work. So, and then once you get to the empty list, you are able to get this bottom, the base case, okay, that's going to return you a 0. So the thing will eventually collapse. It's a pain to move up and down. So, okay, so it's going to get you a 0. Where is it? Okay, yeah, we are there. Okay, so we will return a 0 at this point. And now it's the collapsing of, okay, from the bottom all the way to the top. Okay, so the 0, that's gonna give me something here, something here, something here, something here, something here, something here. And that's what? That's actually this line. Okay. Wait, this line, this one. So all the way up to this line. Okay, so we wait. Let me be careful here. So return 0. Okay, that's here. And we are currently here. Yeah. Okay, that's the lose it. So yeah, very systematic. So once you execute this one, go to the next one. But yeah, not entirely obvious. So yeah, so that's the capacity of 12. We use wait. Okay, so earlier we did what? We did 2. So that's the lose it. Okay. So we did 12 using the 10. That's going to be the 2 with the remainder of list of 5. Okay. And then here we're at the other case. Okay. So that's the first time executing the line 13. All right. So yeah, I would say make sure to go through the procedure. So it goes all the way to the bottom, but then once it's getting to the bottom, then that's the first time you are gonna proceed to the lose it line. Okay, but then if you ever want to make everything I would say transparent, you may need to do your own notes because now once again the line 12 is collapsed, but then line 13 there are local variables which are here. So you have a capacity of 12, you have a list of 5. That's actually from this line. Okay, that's subset sum right here. Okay, so use it. You see, use it is a 10. Okay, so that's what you get from this line right here. Okay, so you have computed line 12 from here, but then line 13 gives you this one more subset sum. Okay. Yeah, indeed, it will take you some time to figure things out thoroughly. So and then yeah, that's procedure calls the function again. So uh yeah, then everything is pretty much sort of like a repetition, but very systematically. All right. Okay, so now that gives you an idea, okay, of how the algorithm would execute. So now let's look at the last question. Do you have a conjecture of the complexity of this subset sum function as a list, as a function of its length? Okay, so that's the question right here. Yeah, so let me get it to the notes and we can write something on the screen. So let me start the sharing here. So now what do you think? Let's say our string here is a length of n. Okay. So let's say this one has a length of n. If I have a length of n and in the worst case, so in computations, okay, in computation theory, or basically you're asking, okay, for a program or for an algorithm that I have this n elements in the input, okay, and then what's going to be the worst case computational complexity to get to the actual answer at the end? So that's the question here. So do you have a guess? N factorial. Okay, so that's one answer. So what do you guys think? Does that sound reasonable? Or do you have another idea? Yeah, so let's think about this. Let's think about this process a little. Okay, so basically you're saying, okay, let's give it a bound. So let's say f of n is the maximum operations. Okay, here by operations we mean addition, multiplication, so those computationally costly operations. Okay, so if you are pending on this, that's actually not that bad. Etc. Okay, for input of n n element string, list. So now, if you think about the procedure right here, okay, so you actually, when you have n plus 1 elements, then what does it do? So basically, it will go through this first condition because, of course, you have more than one element, all right? But then what does it do? So it will give you a list of one element, and then it will give you the remainder, which is n elements, right? So here, the splitting of the list actually is also really cheap. So there's not much of numerical computation that you need to do. Okay, but then you have what? You have the comparison. So that comparison is actually done sort of like simultaneously. You are doing what you're doing first minus the cap, and then you check whether the sign is positive, 0, or negative. So that's actually sort of like a one operation, which is also not bad. Okay, so now you would need to branch. Okay, so here notice the rest list has a length of n. So if fortunately enough, then those computations, okay, these two lines will require you something much less than f of n. But in the worst case, it's possible that this one and this one, they both give you f of n complexity. Does that make sense? We're not talking about the upper bound, right? So you can say this is f of n plus 1, okay, is upper bounded by some constant. So the constant basically just is taking care of the computational cost of doing the if conditions above, and then splitting the list, and then doing the comparison for the first and the cap, right? So that's some constant c plus 2 times f of n, right? So this 2 actually here is sort of like a geometric growth. Okay, so now to get the actual bound, I can do this trick. So I'm adding c on both sides. So this is very common. So this tells you f of n plus 1 plus c is upper bounded by 2 times f of n plus c. And now if you look at this expression, this is more related to the geometric growth, right? So doubling every time, right? So in reality, this is f of n plus a constant is upper bounded by 2 to the n multiplying by f of, let's say, 1 plus c. Wait. So yeah, well, it's n minus 1. If I'm careful enough, okay. So decreasing from n to n minus 1 is one time, doubling once, and then decreasing to n minus 2 is doubling twice. Decreasing all the way down to 1 is subtracting n minus 1 once. So that's doubling n minus 1 times. So this is indeed a geometric growth, exponential growth. Okay. So so this is a bound that's a little bit tighter than n factorial. But still, yeah, it's gonna get more and more expensive. Okay. And if you really think about it, basically it's saying okay, every time my larger, okay, so this is the f of n plus 1 right here. The most expensive computation is that, okay, it branches into f of n and f of n. This is the use it. and lucid. Okay, so these two cases that are calling you a subproblem that in the worst case will give you f of n complexity at the same time. Because now if you think about f of n, you also need to branch into lucid or lucid, right? And f of n minus one as a subtree also breaks into two. So this is sort of like the binary tree. Okay, so let's say we have, so to quickly give a figure, so let's say we have f5, right? That branches to 2 f4, and then f4 branches to 2 f3. Now it just gets ugly, right? So f3 branches to 2 f2. So you see this is the, well, you may not be familiar with this concept of binary tree, but that's basically the idea. So now f1, unfortunately, in the worst case, you would have to branch it to two f1s, just repeats. Okay, so it's what, it's one call of the function, but now it gets two calls, and then 4, 2 to the 2, 2 to the 3, 2 to the 4, and then finally I need f of 0. Because if you remember, the base cases are actually with length 0, so you return a 0. So unfortunately, you would do 2 to the 5th. Okay, so that's actually pretty expensive. So these are sort of like the binary tree, and unfortunately, in the worst case, okay, if the optimal solution is not that easy to search, then unfortunately it's possible to get 2 to the n, which is exponential. So what does it mean? It means this program, although it works, okay, but it works for a list that's not too long. Okay, if it's too long, let's say 1,000 elements, then it's going to be 2 to the 1,000. It's definitely going to blow up. Right. So that problem here is what's called a exponential growth, which is unfortunate. So in our current stage, you would say the computational efficiency is actually good if your complexity here, this f of n, if it's a polynomial expression in terms of n, if you have like a fixed degree. But even if you have degree, let's say 3 or 4, that's still expensive, not very scalable. So when I talk about f of n equal to the order of 3, I'm talking about linear algebra computations. Like if you have ax equals b, where you have n variables or n constraints, then the computational cost of solving that linear system is actually n to the 3, roughly speaking. That's still not fast. Okay, so if in the future you ever get into the course of 591 optimization, there's what's called the interior point method, solving convex optimization problems. So the terms may sound intimidating, but the idea, the bottom line is that they have an iterative procedure. So the convergence is fast, but every iteration they would require to solve a linear system of equations, which is a cost of n to the 3. So really, whenever you talk about the state of the art, okay, whenever you talk about state of the art algorithms, if you can beat n to the 3 or n to the 2, then that's going to be much more scalable than solving linear system of equations in the substeps. But like you see, we talk about linear algebra a lot. Okay, so those are really fundamental computations that you have to do for scientific computing tasks. Okay, so uh, and right, what else? Uh, okay, so let me write it down. So linear algebra, yeah, linear algebra problem. Let's say ax equals b. Okay, for a in R n by n, b in n R n. This is usually in the cost of O of n n cubed. Okay, so that's sort of the complexity of solving it. So not very scalable. Now, so why are we successful in the realm of large language models? Why are machine learning methods helpful? They are actually they can be efficiently computed because in those situations you have high dimensional functions you are trying to minimize. So yeah, let me change to another letter. So this is sort of like a overview, okay? Uh, the topics later you may see more material when you get deeper into the data science program. But basically, you are trying to minimize a function, a g of x, okay, in terms of n-dimensional input. Okay, so it could be billions. But why can it be computed? Because in current days, we rely only on the gradient descent method. So we compute the gradient of the function. In fact, for current days machine learning, well, packages, I would say, they design the network structure or whatever model structure that the computation of gradient is as expensive as evaluating the function value. Okay, so evaluation of g of x is in the order of O of n, which is linear comparing to the data. All right, and then computing gradient fortunately is also in the order of the dimension. So it's not that bad. Okay, if you have n to the 3, then you cannot handle a model of size billions. But for gradient methods, you can. Okay, and then in general, so they may not be able to get you the optimal solution for this minimization problem, but the step that you do is x plus. The new update is actually x minus some multiplier of the gradient. Okay, so so this is why it's not too bad. So x is a vector that's long, that's super long. Okay, possibly n-dimensional, billions, could be billions of dimensions. This is something that's costly. It could be a large number, a constant multiplying by the dimension, which is usually the bottleneck. But then you need sort of like a manipulation between the original data or the current data point and the new information. Okay, so the gradient is the new information. Okay, so you can say this is the uh, suboptimal, and that's the new information. And of course, in reality, you would have many different kinds of variants, okay, of gradient method. But the bottom line is this sort of like simple idea. And of course, in courses like 591, there will be arguments of why this kind of procedure would work for optimization problems. Okay, and then for 592, you will see different kinds of methods that help you to achieve optimal solutions or local optimal solutions, which is eventually really highly related to this procedure. But now you see the bottom line here, okay, very important takeaway is that the power to the dimension, that's very critical. The lower the better. All right? Does it make sense? Okay, the lower the better. So why are we able to solve those large language models to consume, let's say, possibly all text and video and uh, image data? Because of the computational cost. Okay, it's not super bad. Okay, and then for high degree, for convex computation, so this realm you can do computations, but you are getting closer and closer to suboptimal solutions. the realm that's sort of like circled in ellipse, this is the realm that you possibly can get very, very accurate optimal solutions, but it's very costly. All right. And then a little bit higher up for that subset sum. Okay, so if you think about the idea of the problem, okay, you say, okay, I have a bunch of integers as volumes, but I have a capacity. This is sort of speaking a really natural and seemingly simple question, but it falls into the category of discrete optimization. In discrete optimization, it's unfortunate that solution procedures easily gets to combinatorial numbers in terms of complexity. Because if you think about the functions that we look at below, okay, linear algebra, okay, that's continuous. For gradient descent, you are looking at the continuous function. For discrete optimization, it's easy to get into the situation where you branch. Whenever you branch, everything just gets exponential or combinatorial. So that's a realm that's super challenging. So unfortunately, certain things can be exponential. Right. So that's sort of like the overview of certain different kinds of tasks. Right. So for discrete optimization, it's easily that you will get into a problem that's actually really expensive, computationally speaking. Right. Okay, so yeah, well, that I think that pretty much finishes the live coding section for 5. Um, yeah. So yeah, well, the more you see, the more programming courses that you take, there will be more discussions on this kind of computational complexity. Especially if you are taking a course from the computer science program, but here you have a taste. You have a taste of what's going. All right. Before we move on to section 6, any questions?
These fewer steps that is the previous version. It's just two if else if else if else.
This is so for the subset sum problem that we are discussing right now. In fact, there are improvements that you can do, but one unfortunate answer to your question is that this problem is what's called MPE complete. This is actually a very, very deep question in this realm of computer science. So we just mentioned, okay, if you are able to solve a problem in polynomial time, that's ideal, even though the power may be large, right? So yeah, let me quickly write that down. This is very unfortunate. So this is sort of like the bottleneck of human intelligence or computer science intelligence in a sense. So there's what's called a P problem. There's an MP problem. So the family of P problems, they are polynomial time solvable. There's an MP problem. So it's sort of a little bit complicated, but let me put it this way. So you don't know a way to solve it polynomial time, but you know how to verify if the answer is polynomial time. So basically for this problem, you give me an answer. I can tell you in polynomial time that if your answer is correct or not. That's pretty sad, but that's sort of like the best hope that the human can hope for, right? So if you give me an answer, I cannot even verify if that's correct or not in polynomial time, then that's not even tractable for a human being. Does that make sense? So there are the P problem is sort of like a simpler problems that we are able to computationally solve, even though they may be really expensive, but still like n to the 3, n to the 6, n to the 100, that's still polynomial. So that's expensive, but that's what's called the polynomial time. This is non-deterministic polynomial. So for these terms, make sure if you're interested, make sure to search. Okay, non-deterministic. So what does it mean? It just means, okay, I'm not able to solve it polynomial time, but I know how to verify if the answer is correct in polynomial time. So now, why am I doing this digression? So my answer to your question from earlier is that very unfortunately, this problem goes into it goes into this family. So for a problem of size n, possibly large, at the moment, what we know so far is that it's what's called NP complete. So if you're able to solve this problem in polynomial time, you'll be able to solve any problem in this family in polynomial time. That's really a surprising result. Basically, you're saying for those hard problems, NP, if I'm able to solve subset sum problem in general efficiently, I'm able to solve that very challenging set of problem, NP, efficiently. So they are sort of like the same level of difficulty. Yes.
So it's kind of like proving with induction.
Um, that's a good point, but it gets a little bit more complicated than that. But indeed, for this kind of computational cost problem, that yeah, induction is very, very powerful and useful tool. But that's very much a very deep problem in computer science. P problem, they are simple. NP, they are the best that we can solve for. Okay, in using computers, are they similarly hard? That's something open. Okay, so we don't know. So there are ongoing researchers asking this question, and people are just banging their heads on this question, like a conjecture where that NP equals P, but no one has solved it. And our subset sum is a problem that's in the NP realm, and they call it NP complete because if you're able to solve it efficiently, then you are solving every problem NP efficiently. Okay. Yes.
So we're talking about discretization. I'm just trying to relate this back to math to make sure I understand. Because I understand for some differential equations, we can use that technique. We can't solve it explicitly. We can solve the iterative map that's produced from discretization. Is that sort of what you're getting at? Yeah.
Discretization for PDE is more or less like you have continuous problem, but you are using discrete data to approximate a solution. That's what's called the finite element method, right?
Yeah.
Yeah. So I would say that's a numerical technique. That's a very good point, but how does that relate to computational complexity? I'm not 100% sure. But I would say finite element method, I actually have a little bit of experience on that after taking a graduate level course. So I would say based on what I know, solving the PDE problem is expensive, but usually, yeah, well, it's sometimes exponential time, sometimes it's polynomial time. It's really up to what kind of problem you're dealing with. But whether that directly relates to this kind of NP or P, I'm not 100% sure.
I'm just thinking about it.
Yeah, that's a very good point. Yeah, I can confirm that discretization is related to what's called the finite element method, approximating the solution to PDE. Yeah, indeed, because if you think about it, a continuous problem is just harder to solve. So you try to utilize finite data to construct certain systems of things that can be solved by, let's say, linear algebra. So yeah, a very good point. Yeah, subset sum problem is hard. So we don't in the we don't even know if there is a super efficient polynomial time method or not. We don't know. So, or we cannot disprove that there is one. Okay, so is there one polynomial time? We don't know. Can you prove that it's not polynomial time? We can't. Very unfortunate. So yeah, this is kind of like a question that you can ask to a professor who has done some discrete optimization. So, but yeah, um, all right. So yeah, any other questions? We can go back to live coding part 3 if you'd like, because I think there are 2 questions that we didn't actually do, but we can of course certainly look at those, and then we jump into section 6. So yeah, let me quickly mention what my approach would be for the cube root. Where is it? So this is the square. So yeah, this is the square root. So yeah, well, for these codes, I would say think about ways that you can branch. Okay, so traditionally you probably would want to branch to get the solution. So let's say this is the cubic root, cube root, and so let's say for here it can be negative, can be positive, right? For either way, you're gonna get an answer. So I'm gonna say let's let y be the absolute value of x, which I should be able to call, and then now I'm gonna do the search like we used to do. So you're gonna have a guess value, you're gonna get it to the cube of it, and you want to approximate y, and whenever you want to whatever you want to return, you return depending on the sign of x. Okay, so if right, so yeah, I can do it like this. At the end, I return guess, but then if yeah, just like that. Okay, else return guess. Okay, so if x is less than 0, okay, that's good. So what else do I need? If the error is larger than epsilon, then I just keep on running. If the cube root, so here I'm just for the sake of my sanity, I'm making this branch. Let me think. So actually here, one thing unfortunate is that I'm not even sure if the cube root is always less than 1 plus x or not. So let me do the branching here. So this is of course, if you want to do a smart choice of the lower and upper bounds, that's totally fine. But here I would say if y is greater than 1. So now think about this. If y is greater than 1, what does it mean? Well, 1 less than y. Let's do this. Then the cube root of y actually will be less than y. Okay, in this situation, it will be greater than 1. So I'm doing this to get a smart choice of the bound. Okay, and in the other case, I would say else. That means what? That means actually the cube root will be So y is actually less than 1. Less than 1. Between 0 and 1. Okay, so it could be 0. But then remember, if you have a number is less than 1, the cube root actually is larger than your y value. So let's say, for example, 1 over 8, right? So 1/8, the cube root is actually 1/2, right? So you may expect that the root that you get is actually larger. So now if you look at the bounds, these are the bounds that you can choose to enclose your original answer. Okay, so those are the bounds that I'm going to copy and utilize. The main body of the code doesn't change at all. Okay, so that's the idea of using these stuff. But of course, you need to make sure that the indentation is fine. So let me quickly mention what the high level idea is. Okay, so but firstly, so let me take the absolute value of x. Okay, so if it's, let's say, -8, I want to get -2. But then I don't really want to make too many branches. I would say, okay, I just take the absolute value of 8, -8. I'm get an 8, all right? And then I take the cube root, and then if it's negative, and then I flip the sign. So that's the high level idea. And then, okay, if y, so of course, in the square root function, you can also do this branching. If it's larger than 1, your bounds are obviously between 1 and y. That's going to be your left and right. So that's going to be my 1 and my y. All right. And then now I take the midpoints, and whenever I approximate, so yeah, now everything's y. So whatever I guess, I match it with y, and then if it's less, then I change the lower bound. If it's greater, then I change the upper bound, and just continue running. And similarly, for the other case, I have y less than 1. Okay, when y is less than 1, the cube root is going to be larger. So the lower bound is going to be y. The upper bound is going to be 1. And I'm going to match with y again, and I'm going to compare with y again. So make sure to make your bisection search reasonable. Okay. Question? So yeah, this is one way. Okay, you can do some alternatives as long as it makes sense.
I just did the bound, like I didn't take the absolute value, I just changed the bounds depending on if x was negative between 0, 1, and greater.
So my answer to you is that actually, regardless, let me think.
Because then in the while statement, you take the absolute value, so I didn't think it mattered if x was negative.
So yeah, let me
Because the x cubed would end up. It's end up being positive to check with epsilon because you're taking while absolute value.
Unfortunately, I don't have a marker, so so my answer to you is, if you want to do bisection, actually this way to do it is not completely necessary. You can do alternatives, but you want to make sure one thing. So the left bound, the right bound, whatever number that you choose, you want to make sure that it's always enclosing the actual cube root. Okay, so that must be sort of guaranteed. So let's say
if x is less than 0, then your left bound is x and your right bound is 0. If x is between 0 and 1, your left bound is x and your right bound is 1. And then if x is greater than 1, your left bound is 0, your right bound is x.
I don't see a problem.
And then I didn't have to put all of the same, like,
Mm.
yes, yes, wow statements all underneath each level. It just.
Oh, that's what you're saying. Okay. That's a good point. That's a good point.
Statements in that loop and have that copied underneath every
A
single.
very good point. A very good point. So let me stop the sharing for this page and go to the notes. Okay. So here I'm gonna put it at the end of section 3. Okay. So you're saying so if y is so yeah, so then let me just put it on. So definition of cube root, right? So that's your function x, and you're saying when if x is larger than 1, what do you do?
A left is 0, right is x.
Left is 0, right is x, and then what else? Between 0 and 1, and then what do you do?
Left is x.
Left is x, right is 1. Okay.
If it's less than 0, basically, then left is x, right is 0.
That's actually a very good idea. This is a very good idea. So
Maybe 0 and -1 greater than -1. I don't think so, because whether.
I'm thinking about it. I don't see a problem. I mean, on a higher level, if you fix the just basically predetermine the lower bounds and upper bounds enclosing this cube root, and then let the algorithm run below, that's totally fine. As long as your bounds enclose your actual cubic root. Okay. So, but well, on the high level, there's no problem. But I think I can find you a counterexample. Between 0 and 90. So yeah, if you want to fix a branch, you what do you want to do?
So then I just need another LF so that if it's between, yeah, and fix my bounds for it being between -0 and -1. Okay.
Between 0 and -1. And else, right? Something like that, right? So, yeah. So this is where you have x less than -1. But one thing to ensure is that make the bounds coded correctly. You could have separations. Okay, so let's say this is greater than, then you'd want x greater than or equal to 0, and x is less than or equal to 1. So something like that. So then follow with bisection. That's fine. That's a very good point. So yeah, but make sure that make sure your left and the right bound, they enclose your cube root. Okay, cube root of x. So that's something you need to guarantee. Otherwise, you would fall into some issues. So which is why in the beginning I did 2 branches for the absolute value. But of course, if you want to get the bounds predetermined, then run the code. So you do not have repeated code. That's totally fine. That's a very good observation. So let me also adjust my code so that that works. Okay, so but yeah, this kind of procedure. Now that you mentioned this, so I would say you guys will be comfortable seeing this kind of thing when you get into exams. Yeah, so that you see these code cell these blocks are completely the same. Okay, so I'm gonna remove certain things. They are actually exactly the same from before. So number of gases is always 0. and you do the midpoint, and then you less than y greater than equal. Yeah, right. So yeah, these are all the same. So I don't really need that many conditions. So I need to lower the indentation here. Have out. Wait, where's it? Wait, okay, so yeah, let me quickly get a number to be tested and be done for today. Okay. The cube root of -8. Let's try that. I'm expecting to get a -2. Okay. Yeah, good. All right. So yes, so yeah, I would say in the exam you can certainly expect something like this. Okay, so determine the lower upper bounds up front, then go through the bisection is totally fine. Let me try something else. So point 1, 2, 5. Let's say that's 1/8. Yeah, good. All right, so yeah, that's pretty much it for today. So we'll continue on section 6 on Monday.